Oh, scoping chapter 6, applications of quantum mechanics. Quantum units, particles or waves, quantum states. How can we use these quantum units in real life? Apply them. I think we've seen some applications. X-ray crystallography, spectrum tubes. Well, I suspect it's mostly electronics. Let's see what this is about. Practical consequence. Wave function, barrier thicknesses, some wave, and there the wave is changing in it. We've got some barrier. Quantum particle, so using the wave nature so it can actually go through a material. One of that applies to light, photon. You get material that is, I don't think that's what you have with a light passing through a transparent medium. Edge of the barrier, wave function that may fall to exactly zero, insufficient energy, so called tunneling. So it's something about the energy and passing through some barrier, quantum tunneling. Quantum tunnel, wave function. The wave function, the wavelength depends on the momentum. Do you want a long or a short wavelength in order for it to pass through? Exponential decrease inside barrier, quantum tunneling. Tunneling out of an atomic nucleus, quantum tunneling. So what is this about? The nucleons are not supposed to escape from the atomic from the nucleus, nuclear particles inside of it. But here they're suggesting under certain circumstances it can escape, it can get out. Non-zero amplitudes, nuclear force, yeah. So quantum tunneling, it shouldn't escape, but it does happen due to the quantum nature. Something about the wavelength. They're concentrating here on the de Broglie wavelength, depending on the momentum, whether it can actually get out. So, escaping from the nucleus. All of these particles are inside of the nucleus. Quantum tunneling of an alpha particle from inside an atomic nucleus. That is radioactivity, isn't it? Alpha particle. So are they suggesting that it happens because of the quantum nature, that you get radioactivity? Alpha radioactivity, alpha waves, beta waves, gamma radiation. So those are the three types of radioactivities you get. Nuclear energy, well, so it's escaping. It seems it's about escaping, getting outside of the nucleus, quantum tunneling. And here is something about electronics, a tunnel diode. Diode, electric current. So is it about the electron moving through the diode? So radioactive tunnel diode. So they just shortly mention the tunnel diode. Tunnel diode relies on quantum tunneling of electrons at the junction between two materials to provide a weak current in a semiconductor. So the electron passes through that junction due to the quantum nature. Imaging atoms, platinum atoms, photograph an atom, field ion microscope. So use ions, high voltage ions emitted by the tip. This looks like an interference pattern. So here comes the somehow ions that got a tip and high voltage, I think. And there is some ions formed near the tip, and they use their wave nature to form these diffraction patterns, and that tells it something about the material at which the tip is brought to. Field ion microscope. So it's a nucleus, diode, imaging, image of atoms. So the atoms are in a crystal lattice, and that gives you the diffraction pattern. So this diffraction pattern tells you something about the atoms in that crystal lattice. STM, scanning tunneling microscope. Again, imaging atoms. So using scanning tunneling microscope. Again, a tip of a needle, tunneling current. So it seems it's electrons. And the electrons interact with the material, and you get what's great one, moving individual atoms using STM. So manipulating atoms with a needle, actually shifting them around, positioning them. What on earth? Okay. Imaging electron orbitals. So it's quite a lot going on here. Atoms on the surface can be moved by the STM to create atom-sized machines. It's like almost they've built a gear here with the atoms. Electron orbitals, wave function, probability, electric field, image of individual electron orbitals. Somehow it seems they can view the electron orbitals. Somehow. I can't make out how they're doing it, but that's viewing the orbitals. Quantum microscope. Used laser beams to ionize atoms and trace the electrons. Something about a laser and a quantum microscope. Quantum microscope use laser beams. So it's photons interacting with matter, and somehow they can view the electron orbitals. The laser is just, I think, it's very narrow wavelength. It's a very specific wavelength. It almost sounds like the optical setup for diffraction. Viewing the electron orbitals with a photon beam. Quantum computing. Quantum computer. What on earth is going on here? Quantum computing. Where am I time-wise? 11 minutes. Computers, on-off switches, binary mathematics. Switches. So in this case we've got quantum states called bits. Fully on or fully off. Algorithms. Run them concurrently with other calculations. Parallel computing. Greatly improves the speed of arriving at the final state. Parallel computing. This is what is happening here. Quantum computer. How is this parallel computing coming about with the quantums? Input and output, get the final answer. Quantum states. Connection between an input and output. No idea what's going on here. Richard Feynman, Yuri Manin. Normal computers, bits, algorithm, operations, calculation, quantum computer. Algorithm takes all possible paths between input and output state, and quantum processes of superposition and entanglement. So they're using superposition and entanglement to somehow perform algorithmic calculations or algorithmic processes. Qubit. Quantum computers. Cryptography, folding of proteins. So that is the type of computations that can be done with the quantum computers, it seems. They take multiple paths due to the superposition states. All possible solutions. Largest quantum computer to date is the IBM Q System 1, 20 qubits. Creation of large will have to confront the very difficult and sublime is called the problem of time. Okay. Where are we time-wise? 14 minutes. Quantum tunneling. Radioactivity, tunneling time, half-life, energy between the particle and the energy barrier. Quantum tunneling, getting out in spite of probably not having enough energy. imaging atoms, and then they also imaged electron orbitals and manipulating atoms. One of the quantum processes are involved there. Quantum computing. Input and output states to be placed in the entangled state. Ooh. The input and output are entangled. Effective samples all logical possibilities at once to find a effective samples all logical possibilities at once to find a solution. All logical possibilities. Entangled. Input and output. Advances in quantum computing hinge on answers to very deep questions in quantum physics. Such as the origin and interpretation of time. So they're doing things, but it seems they don't understand it. That's the idea I get. Hinge on answers to very deep questions. It's working and it's doing something, but how it works, they don't know. As well as this distinction between the input and output states of a problem. Okay. Quantum tunneling, imaging, and quantum computing. Imaging atoms, manipulating atoms. Going through materials where it shouldn't do that. It doesn't have enough energy to get out of there, but it does. And then finding solutions, special computers using quantum units in superposition to find answers to problems. Okay, that's about it.